Hello, everyone. Thank you for being with us. And it's going to be our next session in stage two. It will be a talk 2 4 hour conference. Okay, when we talk about software-defined vehicles, talking about security testing and its challenges is unavoidable subject. We have speakers on stage who going to talk about how fuzzing and proposed solution can help to solve some of these challenges. Without a further delay, let me introduce to you our speakers uh, Rakshith Amarnath and Khaled Yakdan. Rakshith is currently the director of embedded and automotive solutions at German startup Code Intelligence. He brings more than a decade of experience in automotive sector. He's been given the talks into multiple communities and been into industry chair for IEEE conferences. He has a background of MSc degree in embedded systems with honors from Delft University of Technology. Khaled Yakdan is the chief of scientist and the co-founder at the Code Intelligence, holding a PhD in computer science and having spent over 9 years in academia. Now oversees the implementation of research outcomes in AI, usable security, and vulnerability detection into Code Intelligence products of Code Intelligence. Please welcome Rakshith and Khalid on stage. Over to you, Rakshith and Khalid. Stage is yours.
Hello, everyone. Good morning, good afternoon, wherever you are. Hello from Code Intelligence. I'll straight away start by telling you the backstage story that led to this presentation. So, as you all might have observed, the automotive industry is going through a really interesting revolution. This revolution is happening not just because of the trend towards auto electromobility, but also the fundamental way in which future cars are leveraging computing and software is changing. This revolution, which the industry now calls software-defined car, mainly influenced the title of this presentation. Automakers nowadays are going all in to make cars similar to smartphone on wheels. And against this backdrop, I thought of telling you why software security is facing the tragedy of the commons. In this presentation, you will initially see me. I'll set the stage for Khaled, who will present in more technical manner later and also show you a demo. And we love this ASRG community, which deeply cares about cybersecurity for cars. So I would say Khaled and myself are really looking forward to the questions from you. Keep them coming. We'll get to it. So in the initial part of this presentation, I will touch on a few topics. I'll first start by revisiting the real-world examples of software vulnerabilities which lead to remote attacks and calls and recalls. And then I will briefly talk about security testing challenges which are faced by the automotive enterprises that are trying to build the next generation of software-defined vehicles. I will then reveal the reasons behind why I was trying to equate software security with the tragedy of commons by introducing a term called checkbox security. And lastly, I will set the stage for Khaled by telling you what the role fuzzing is playing in improving security and also the challenges it is facing on its way towards being adopted in the automotives. So let's get started with a short list of real-world cybersecurity incidents. So the first real eye-opener, you all might know, Jeep hack keeps being, used and reused in many, many conferences, is the Jeep hack. And this allowed one to remotely hijack a car by exploiting software vulnerability in the in-vehicle connectivity system. And earlier this year, a really famous research was done by Sam Curry et al. It showed how insecure API endpoints in vehicle telematics could facilitate fully remote attacks. And last but not least, talking about real world impacts, it's also like, I think sometime in 2020 or 2021, there was this T-bone attack, which allowed attackers to take full control of the infotainment system of a Tesla with zero user interaction. So all of these real world incidents show the real world impact of software vulnerabilities in cars. And in order to make sure that software vulnerabilities don't end up in the field, effective security testing needs to be in place. Now, why hasn't the automotive industry caught up with cutting edge security testing? So as you see, there are some challenges on the way. With the goal of making smartphone cars also smartphone on wheels, automakers are increasingly turning towards software these days. software has become the key ingredient and the main differentiator for software-defined vehicles. Furthermore, cars are also becoming increasingly connected to the internet on all levels in order to facilitate software over the air and to keep functionalities fresh and up to date. In order to do this, car makers are turning their proverbial manufacturing units into agile software production platforms. Notable examples of these are BMW's Codecraft, Volkswagen OS, VW OS, and even Mercedes-Benz OS, MB OS, etc. For all this to happen, the automotive industry has to adopt now. They have to adopt and also build on modern software engineering DevOps paradigms. This duo of software centricity and connectivity is leading to an increased attack surface from a security point of view, and this is also making DevSecOps, which is the sandwich of security between DevOps, all very, very relevant these days. However, the scalable rollout of DevOps in automotive is challenging. This is because automotive industry comes from a huge history of being firstly oriented towards mechanical innovations, then moving towards electronics. And there's a huge complexity because of this legacy use and heterogeneous software supply chains, which is being provided by multiple tiers, and also the increasing need to fulfill safety critical requirements. It's now time for me to tell you why I use the terms software security and tragedy of the commons next to one another. One of the most pressing challenges car makers are facing these days is to integrate security testing into the software development process. It is still challenging today because automotive software developers need effective techniques on one hand and easy to use tools on the other in order to improve software security. Now, why is it that security is not sufficiently prioritized, you might ask? It turns out that security is not the only concern for car makers. The concerns are multidimensional in nature, and there is enormous pressure to be cost efficient as well. The multidimensional topics which car makers face range from rolling out DevOps to long-term maintenance topics. Also, fulfilling safety standards and handling variants are further concerns that automakers have to manage, and there are several trade-offs on the way towards designing cars. As a consequence of these trade-offs, they show up in a way in which it makes it difficult to go for proactive vulnerability discovery during DevOps, and that's why it's taking a backseat. On this front, vulnerability identification is still happening on penetration testing, but if you see the costs involved and the round-trip time needed to fix issues found during pen testing, it's quite high. And when it comes to software security as such, at the moment, only coding guidelines, adherence, and reactive-based vulnerability management is done. And at the same time, the industry is facing enormous normative pressure. If you see the ISO and SAE standards putting more pressure, you see that they're requesting more and more rigor in doing security during development. And due to the lack of easy-to-use tools, the normative requirements are being fulfilled with as little effort as possible, something we call checkbox security. It's kind of a derogatory term, if you see, because security testing gets reduced to merely an exercise of checking the boxes. So we have seen conflicting objectives on one side, checkbox security phenomenon on the other, and the hot potato of software security now gets thrown to developers who are now made responsible to ensure robust software. But sadly, even they cannot address the problem as a whole because they are grappled with islands of expert tools that only address partial aspects of secure software development. And this is the reason why I termed software security as the tragedy of commons. Quite a sad state of affair, you might think, but there is hope because on the other side, there are modern techniques. Those are also proving itself to be easy to use and very effective in securing software. So this now brings me to fuzzing. So fuzzing is one of the most effective techniques out there to find software vulnerabilities. If we rewind back a few years, there were discussions around how fuzzing could have prevented critical vulnerabilities like Heartbleed. Heartbleed in practice is like a read buffer overflow during execution, and this could have been easily caught with modern fuzzing. This blog, which you see here, came out in 2014, and it made an interesting prediction about fuzzing being able to find other bugs in future. And boy, fuzzing has come a long way since then. Pioneers in applying fuzzing at scale in practice are IT giants like Google and Microsoft. Google's OSS fuzz has helped identify and fix over 10,000 vulnerabilities and 36,000 bugs in over 1,000 projects. No wonder why Android recently decided to go all in on fuzzing. Now, enough of social proof. What on earth is fuzzing? If I were to explain fuzzing to my dad, I would use a simple metaphor from the advertisement industry. So back in the 90s, advertisements were randomly put on billboards with the hope that someone saw them. But nowadays we have social platforms, social media platforms, which target highly specific advertisements to the users. The targeting of advertisements is possible these days because we have techniques that allow social media platforms to observe what a user is doing online. The same principle applies to fuzzing as well. Modern fuzzing tools can observe the software during execution to target specific test cases during execution to expose critical software vulnerabilities. Now, everything sounds good, but yet applying modern fuzzing to automotive software is not straightforward. This is because automotive software has a few peculiarities, and these peculiarities range from the code being architecture dependent, the code being stateful, as well as few other challenges that create the need for high expertise and also create a really high barrier for adoption. I must say now the stage is set for Khaled, who will introduce fuzzing more technically and show you approaches of how system and module level fuzzing lowers this entry barrier for automotive software. Over to you now, Khaled.
Yeah, thanks, Rakshith. And now I can share my screen. Okay. Yeah. So as we've heard, fuzzing is a very effective method to find critical bugs and security vulnerabilities in your software. So now let's have a closer look, a closer technical look on what fuzzing actually is and how we can address the different challenges when applying fuzzing to automotive software. So at a very high level, the main idea of fuzz testing is very simple. So you have a system under test, and then you have a fuzzer that just feeds some random inputs into the system, hoping that you find a given input that leads the system to crash. And this would mean that you found a test case that causes a crash in your system. And this is how fuzzing started in the late 80s. But if we pay a closer look into this scenario, we see two obvious limitations. Well, first, doing this random test case generation in a black box manner makes it hard to reach deep bugs, meaning that imagine that you have an image parser that expects certain images, and it's very highly unlikely that a black box fuzzer would just generate valid images. So doing this black box limits the code coverage significantly. And the second issue is that not all bugs or security vulnerabilities would lead to a crash. Rakshith mentioned the heartbeat vulnerability, but you can use a read buffer overflow to read some sensitive information. This doesn't lead to a crash. So we need better ways to find bugs in software. And so there has been several works and advancements to address these two issues. But the real breakthrough with fuzzing came with the idea of using feedback from executing the application in order to guide test case generation. And the main idea is quite simple. So when we build our code, so we instrument it, meaning that we inject certain markers into the code that would give us or give the fuzzing engines feedback about which code has been covered, which values have been compared, which program state have been reached, and all this information, all these signals will be used by the fuzzer to do smart mutations. And how does this look like in action? So imagine that we go back to our image parser example, and then we start with the fuzzer starts with zero knowledge about the application. So it starts with just some random number, and it gets a report similar to this one. So in green here, we see all code lines that have been actually executed. So we see that we have two if statements. Of course, none of them are valid because the input is invalid one. So the fuzzer would get, okay, this with this input, I was able to reach these code areas. But also, I get the information about that my input was compared against these constants or these magic numbers, like FFG8. And one of the smart mutation is that the fuzzer would then try out is that use this constant in subsequent iterations. So now I can just try out these constant and see if with that I would reach new code coverage. So now when we execute the application with this input, we see now the second if statement is fulfilled. So basically, now with this mutation was good because we were able to reach new code. And at a high level in this case, so the fuzzer has managed to sort of to convince the application to treat the input as a JPEG image. And so as we see that step by step, the fuzzer will just learn through the um, the the expected format of the inputs that needs to be fed to the application in order to reach good code coverage. And yeah, so fuzzers are very fast. They don't get worse. So we can get to hundreds of thousands of executions per second each time we get new signals from the application, and internally um, the algorithms for test case generation, or that what we call it self-learning AI, meaning that um, we don't have to have any knowledge about the application under test, but with this signal that we get from the instrumentation, the self-learning AI will be able to generate good inputs that gets good code coverage. And this way, step by step, we would learn what good inputs we need to generate. And this is actually an actual experiment that was done with one of the coverage guided fuzzers, and where as an image buffer was tested, and quite fast the fuzzer started to generate valid images because step by step it learned about the structure of the inputs. And one extra thing that we add with the instrumentation is what we call sanitizers or bug detectors. And these are runtime checks for certain types of bugs that we get notified even if these bugs don't crash the system. So this is at a high level. So what coverage guided fuzzing is, and this is the self-learning aspect, is that we don't have to have previous knowledge about the application, is what makes it very, very effective in triggering bugs and security vulnerabilities. So at a high level, you can imagine it. If we compare this with the black box approach, is that with the black box approach we have no idea how the application is reacting to our inputs, and we will miss many bugs because not all bugs would lead to a crash. With AI-based white test fuzzing, so we know exactly all code paths that we have tested. So we know exactly what we have tested. We know exactly what we have not be able to reach yet, and we will see much. We'll be able to uncover much more bugs because we have our specialized bug detectors. So from a developer point of view, it would make sense to compare fuzz testing to regular unit testing. So when we develop new functionalities for our code, we hopefully always write good tests first. So we write unit tests, for example, for that. And what our unit tests would do is that we will, as a developer, we will come up with certain concrete inputs that trigger certain cases, and then we test our APIs with these concrete inputs, and we see if we get the expected results. With fuzzing, it looks a little bit different. So we don't have to come up with these inputs ourselves, but we can think of it as a continuous loop, and each time we get a new input from the fuzzer based on its test case generation algorithms in order to maximize code coverage based on the instrumentation feedback. And so what this also means is that for fuzz testing, we would need to write also what we called fuzz test, which is a small test harness that would take the input from the fuzzer and then feed it back to the application or to the API that you want to test. And this is we'll have a look at in a moment. And so we said, okay, fuzz testing is quite effective in finding bugs. So what kind of bugs we can think that fuzzing would be able to find? So of course, we can find a lot of security issues out of the box. And so if we think about automotive software, where we mostly use some memory unsafe languages like C and C++, we can find a lot of memory corruption errors like buffer overflows, use after free, double free. We can find undefined behavior, data races, memory leaks, all kind of these bugs. And these bug detectors come sort of for free based on the bug detector, the sanitizers that we can use. But we also can find a lot of functional bugs. So anytime, like if my application has some assertions, or if I can represent the criteria or the properties of my application that should be fulfilled for all inputs, you can just very nicely write a fuzz test for it that checks for it, and the fuzzer would then be very effective in finding some corner cases where those assertions are not fulfilled. So these are the kind of bugs that we can find with fuzzing. And now, so that I hope that you were able to get like a good overview of what fuzzing actually is. But let's see, how does it look in action? So let's dig a little bit deeper and get more technical and see how we can develop fuzz tests and how we can integrate those into our development lifecycle. So what? Well, first, let's start with the big picture. So let's start of how would it make sense to integrate fuzz testing into your development lifecycle? Because we mentioned that pen testing you can do pen testing, for example, but this is you cannot do it like every day or with each code change. For that, usually you do it like maybe before a release, and this would mean that a developer developing a feature would have to wait weeks or even months to get feedback onto the security of the code changes that he or she has done. And this, so in software development, as we know, quick feedback cycle and short feedback cycles are key to getting things done or fixed very, very quickly. So the way we see the secure development life cycle is where it all starts with the developer, where a developer would then write new functionality, refactor some code, and he or she would write also fuzz tests. And alongside these fuzz tests, or unit tests, and alongside with these unit tests, you can write also some fuzz tests. And then you push your code into your code hosting system. And in this example, we show with GitHub. And what this would do, this would trigger your CI pipeline. And to get the most out of fuzzing, it needs to be done continuously. So your CI pipeline, you can configure it on each pull request or on each change is up to you. This would trigger a code change would trigger also a fuzzing pipeline. So we would then need to fuzz your software. You fuzz your software, and then you get very quickly a notification or a feedback. Okay, now everything is green, or there are some issues with your code that fuzzing has found. Then you can go ahead and have a look at these bugs. And so the good thing about fuzzing is that this is a distinguishing factor from static analysis is that you get 0 false positives. Is that you get for each example, with each finding that fuzzing reports, you get a concrete test case that you can use to reproduce the error. And with that, you are well prepared to have a look at the error and see what went wrong. You fix it, you push your code. In this way, you guarantee that you do this continuously and you get quick feedback on your code. So what do you need to do in order to write a fuzz test? So what we see here is an example of a unit test, or so we're using Google test, and you just write some code that call your API with certain inputs. A fuzz test looks very, very similar. So you would write and this is the case of C and C++. You would write this fuzz test macro, which takes 2 parameters. It takes a data and a size. And data is a data buffer that's generated, that's filled by the fuzzer. So in each iteration, so you can think of it as this code will be executed continuously by the fuzzer. Each time you get a new data buffer, and then you can use this data buffer to call your code. And this data is changed, is optimized by the fuzzer in order to reach good code coverage. And yeah, so maybe before we start having a look at writing a fuzz test, let's see. So we mentioned the CI/CD integration. So how does it look like when a project is integrated or when fuzzing is integrated into a CI/CD? So here, what we see a small example is an automotive example. It's from our repository, and which is open source. You can have a look at. It has few modules, and now we have here two pull requests, and just to show how does it look like when fuzzing is integrated into your development lifecycle. So now I have a first pull request here, which when we have a look, so it has failed. So let's go inside and see why it has failed. And so it has failed because fuzzing has found there's one issue that has been found in this run. So what you can do right now is that say, okay, I want to have a look at this finding. So by clicking here, so you will land in, and so this is, you see the web interface of our SaaS, the software as a service platform. And then you see this is the project that I have. This is the issue that the W3 issue that that's being reported. And then we see a complete stack trace. We see a concrete input. So with this input, you can actually trigger this issue. And then you can have a sort of a description of what went wrong. You can even click here to see the exact location where this W3 has happened, and it's here. And so with this you are well equipped as a developer just to handle and to solve the issue. And yeah, then you would fix the issue, you push a new code change, and now we see everything is green. Then you are actually ready to merge your code. And in this platform, you can also have a look at previous runs. So this is the first one that we found the issue was found, and this is the second one. Now no issues is found, and then you can even have a code coverage report, meaning so in this small project we were able to basically cover everything. Yeah, so this is how does it look like when fuzzing is actually integrated into your CI/CD workflow. And now let's take a step back and see what do we need to do in order to create those fuzz tests. And so as Rakshith mentioned, so this is all good, but for automotive software we have special challenges. So there are external and hardware dependencies. There are special where code can have inline assembly that's written for certain CPU architecture. It's stateful and it has a large code base. And so fuzzing usually is the most effective one. It is run on an x86 Linux architecture. This is where you get the most performance out of fuzzing. So what we will propose here in the next two slides, when we talk about module and system fuzzing, are two approaches where we make it possible to have, even if you have an automotive software, to have a fuzz test that you can run on Linux x86 platform. And so for that, we would start with what you call a module fuzzing. So with module fuzzing, you have a certain module or a group of modules that you want to test. And the approach here, what you can do is that, so obviously these modules, they have some sort of a public API, and these are like functions that are declared and defined here in these units that are supposed to be called from the outside. And these units also might have dependencies, meaning there are external functions that are being called from our module, but they are not implemented by this. So what we can do here is to handle these issues is that we can take our public API, write a single fuzz test that tests all these public APIs. And what you can do is that we test it in a way that for when we write a fuzz test that calls actually this public API with fuzzer generated data. And regarding dependencies, you can generate mocks, or you can write mocks or stubs for these dependencies. So instead of calling the actual dependency, for example, if you have a function that returns an integer, you can just return an integer from the fuzzer generated data. And with this approach, you can guarantee that you have tested basically your module and public API under all possible circumstances. And this is what what I will show a demo for, is that how we can do this. And so in here you will see my the same example that you have seen in on GitHub. So it has some modules, and for example, if we have a look here at here we have a function, an external one that is used by our model but not defined by it. So this represents an example of external dependencies. And so, and also like in the community, or when we talk to customers, so creating fuzz tests is actually one of the most challenging parts that of adopting fuzzing. So what we can do there is that we can so what you did there is that we can use some static analysis to automate this process. So obviously what I will show here, what we do automatically, you can do by like manually, but with this, with our tooling, so what we have is this to automatically automate some of these steps. So what you can do is that we have this tool, what we call CI auto test, that you can use to generate a fuzz test for a given project. So here, if we see here, so when I run this tool, then it will generate for me automatically two files, one fuzz test and one mocks. The mocks are for the external dependencies, and the fuzz test is the one that tests all the public API. And so let's have a look about, as I mentioned, this is an automation to give you a head start, but this is something that you can also write by yourself. So what we do here is the following. So we have a fuzz test. So this is what we have seen so far, that each time we, in a single test, we test all the public APIs. So here you see that we have, what we do is that we generate a loop, basically, that each time we pick, so this is what you call, this is a fuzz data provider, which gives you can use to get some data of certain types from the fuzz generated data, so that you don't have to work with raw bits and bytes. So what you do here is that in each iteration, we pick a public API that you want to test, and then we generate code that basically call this API with fuzz generated data. And since what we need to make sure here, what we do here automatically, because we do static analysis to analyze all the types, is that you, for example, here you need to, for example, here we have a struct. You need to properly initialize it, and then just in some cases, for example, here where you have to provide a buffer and a corresponding length, we give hints of what, for example, here, and by default we generate everything from the fuzz generated data. In some cases, it would make sense to then make the length here corresponds to the actual buffer, because this is what the API expect, and this is you can do because you have sort of the domain knowledge about the application. And yeah, so this is enough. This is the fuzz test. So in each time we pick a chain of functions of public APIs that you want to test, and then in each iteration we just pick a function and then call it with fuzz generated data. Also for external functions, so we've seen this GPS function. So what you do here is that, as I mentioned, for some functions that external ones that would we just for return values, we just pick a value from the fuzzer and then return it. And if the application needs get some buffers that should be filled by the external functions, then as in here we generate code that just fills these buffers from the fuzz generated data. And there are certain cases where we cannot statically know the type, but in this case, so if we see how this function is actually used, we will get good hints about, for example, that this is about the size of the buffers that are used here. So with minor fixes here, you get a fully working fuzz test, and we can also see it in action. Like here, I will then switch to another branch where this is already fixed and set up. So here we have the same fuzz test as I mentioned, but where we actually fix the length. And now we are ready to go. And now, so what we have done so far is that we generate a fuzz test that tests all the public API, and we generated mocks for all external functions. So now we are ready to run our fuzz test. And I will do here with our open source CLI. So all you have to do is that, and this is what we call module fuzzer in this case. And then now when we do this, the CLI builds the code with instrumentation, with the sanitizer, and then you get a report when something goes wrong. So here we have now this finding, which is called, for each finding we give some names, make them easier to remember. So now you can say, I want to have a look at this finding, which is called fantastic something. And this is the same finding that we have found there, which is with we've seen in the GitHub integration with, which is a WP error, and then you get, as I mentioned, you get the complete stack trace, so you know exactly what went wrong. Sorry for being a little bit fast, but just for the sake of time, yeah. And so this is what we call module fuzzing. We have what we do also with other projects is that you can apply this approach on a system level. Like imagine you have a system like AutoSAR, and then what you can do is that you can build a single fuzz test for the whole system. So you compile the whole system as a fuzz test. For that, of course, you would need to sort of replace the microcontroller and the OS layer, because these would not work on x86 64 environments. And for that, this has been proven very successful in practice with our automotive users, and this is something that obviously you can do as well. And there you basically communicate with the application via the outer interfaces like CAN or Ethernet or something like that. So you test the whole application at once, but there you need, it's more involved to show in a demo, but this is we've sort of successfully applying this for complex projects. So yeah, now we come to the end of the presentation. So hopefully we were able to convince you that fuzzing is very effective testing method to find bugs and security vulnerabilities. It's sort of trades your expensive engineering time with cheaper and alternative, which is the CPU time. You just need CPUs to test it, and it can be applicable to complex use cases such as automotive. And from experience, so it's mostly effective when done continuously and not over like longer time intervals. And what we then want to achieve with that is that we don't want to release any bugs similar to Heartbleed that fuzzing could have found previously. And with that, we come to the end of our talk. Yeah, we're happy to take any questions, and if we are also can reach out to us after this event via email, Twitter, LinkedIn, and we look forward to talking to you guys.
Thank you so much, Khaled and Rakshith. Really appreciate that. It was really a great session, a lot of information, and I see our chat is very much interactive with the attendees and you. So I think too many questions, I believe. We have 5 minutes, and Rakshith, would you like to take few of the highlights from the chat where you want to address some of the questions from the attendees?
Yeah, sure, I can do that. So one interesting comment was, I think already someone said, it's already second time that someone is mentioning ticking the boxes. So where is this coming from? So a quick disclaimer here: we are not generalizing that everyone is treating security as ticking the boxes. We won't go that far in making this generalization. The issue came up because security in the end is a shared responsibility, which gets kind of thrown like hot potato to everywhere within the organization. Nowadays, what we're seeing is there are dedicated security people who are responsible for ensuring cybersecurity, and they rely heavily on process methods and tools to be effective. And when the PMT process methods and tools are not effective within an organization, we see symptoms of like saying, okay, what's the minimum thing we can do to kind of get through certain or the other normative pressures. So this is where this is coming from. And the solution to it is to say, okay, how can we as a whole, as an industry, make sure that specific verticals, be it automotive or defense or even medical devices, kind of improve the PMTs and make security people more how do you say capable of handling the security issues and more yeah, exactly. So it's a shared responsibility. That's where this is coming from, and this leads to effective process methods and tools that need to be in place.
Thank you, Rakshit. I think this is the good point to mention here. And uh, we have a lot more questions coming up. And I have one question which I can ask in 2 minutes. Like, what is the current status of virtual automotive ECU to speed up system for testing without expensive hardware?
Okay, let's take it one by one. I see the first one from Isabel. Thank you. The current view on adoption is that we see, as we mentioned, as I also mentioned, software-defined trend, right? So most of the automotive companies, tier ones, OEMs, they're using more and more software in the loop for their development. With this, it's also easy to introduce DevOps, DevSecOps, and really speed through. So the adoption is that it's in an awareness stage where people do realize, okay, the cybersecurity IT community has benefited a lot from many different things. So if it comes to like fuzzing, they also want to embrace that within the automotive development lifecycle. So it's in the awareness stage, going towards like the early majorities are already reacting. We will then follow up with the other ones. I hope that answers Isabel's question. The next one, what's the current status of VECUs to speed up system fast testing without expensive hardware? Yeah, so I can tell a bit about what's happening on the larger side. So this virtual ECUs are the key enablers. If we cannot test ECU software or automotive without the hardware, then we can't really scale up testing efforts. So the current status there as well is that it's in the adoption stage. There are many companies we see who are already having their entire software stack already being, capable of running on a desktop machine, which is already huge step because earlier they used to do only hardware testing. So this is slowly picking up, but not fully there yet.
Thank you, Rakshit. I think remaining questions, we can take it off stage, and due to the timing, we need to make sure like all the sessions are in place. And thank you so much, Rakshit, and thank you, Khaled. We really appreciate that. And guys, please feel free to reach out and drop your questions. You will get your response from Khaled and Rakshit. Thank you all. Enjoy all the remaining sessions.
Thank you for having us.
Bye bye.
Thank you. Take care.
All right.
Bye.